Hello and welcome to antenna array factor model from antenna and wave propagation course. Here we will look at the radiation pattern for antenna array and how it is different than individual element pattern, and we'll appreciate its significance. We'll also understand array factor for antenna array. We'll learn how and appreciate the expression of calculating a normalized normalized pattern for linear antenna array. We'll identify array factor from given normalized array pattern expression. We'll also, using normalized expression, will calculate approximate pattern and draw a radiation pattern by identifying nulls of antenna array. Let us look first of all the significance of array pattern. Most of the single element, when we want to enhance the directivity, we need to increase the dimension of element, because we need normally in practice very directive characteristic of an antenna. So without increasing the size of individual element, assembly of many radiating elements which is forming the array will help us to enhance the directive characteristic of the antenna. Now, how to calculate field of antenna array? It is basically can be done through the vector addition of the fields radiated by individual element. So basically what we are doing is we are adding the fields of two element. Now problem is that this array interference may add constructively or maybe destructively. So the overall pattern may be different than the original pattern. Sometimes it may cancel each other and sometimes it will enhance in some direction. Now control, how to establish a control over a directivity of antenna array. So basically geometric configuration of the array, whether it is linear fashion, it is in a circular fashion, or it may be in a rectangular fashion, maybe in a spherical. So this will help us to decide the directivity of an antenna. The second important factor is the displacement between the elements. So how two elements are placed and how far they are from each other. Another important aspect is excitation of individual elements. So if they are phase shifted from each other, then altogether it would be giving a different value. So the amplitude and phase of excitation plays very vital role in deciding the directivity of an antenna. Then individual elements pattern also plays a very crucial role to decide the directivity of antenna array. Let us now consider two element array. Let us consider two elements. One is kept here at a positive z axis, another is kept here at a negative z axis. Both are kept horizontal, and that means along the y directions. And we are interested in a resulting pattern at this particular point, which is distance r1 from first element and r2 from this. So normally we take it average distance r, considering this point is very far from these two elements. So almost in that case these three distances are almost same, and angle which they will subtend will be like what they will subtend with the origin. Now distance between two elements considered is d, and positive d by 2 on a positive z axis and negative. So first, for such an element, if we take an individual, so let us recall that E and H field for infinite small dipole, which is kept here, these two in a horizontal fashion. So here this expression is for a vertical, so that can be given by as follows. Now H phi, E theta and ER, you can see these are all the terms involved, but for radiation it is very important to look at just a term which is having 1 by R, so which is the first term. So E theta exists for a far field, while these two, which is concluding R square and R cube terms, so these are not important for a far field. Similarly, H phi is the term which is useful for far field, and these are nothing but near field terms, so this will neglect. So we'll consider H phi and E theta in case of the vertical element. So when we look at the present case of the horizontal, we will conclude that the total field will be given by K times I0L e raised to minus jkr divided by 4 pi r cos theta, where theta is the angle subtended here between a line joining from point of consideration to the origin and the z-axis, and the distance r is the distance from point of consideration to the origin, which is a middle point between two elements. I0 is the excitation of the current, K is a constant, theta is a constant, and the theta is the angle at which we are considering the radiation pattern. So as theta varies, we are changing the directions, and then for each value of theta we are interested in what is the radiation pattern in that particular direction. So once we look at carefully the total radiation resultant pattern ET, you can bifurcate into two parts. One is the radiation pattern of individual element, and second part, which is nothing but the multiplication what we are doing to get a total. So this particular term is called array factor. So in short, array factor is nothing but a factor by which we are multiplying with the individual pattern to get a resultant pattern. So in our case, two element, it goes like this: 2 cos of half of kd cos theta plus beta, where beta is a phase shift between two elements, d is a separation, k is a constant which is given by twice pi by lambda. And if we consider a normalized pattern, so here two elements, so we need to divide by 2, but in general if I have n element, I can write this as a array factor for an element like this. Now what are the variables involved in array factor? So it is basically a geometry, so how far these two elements are kept, and what are the excitation of phase, assuming the amplitude of both the currents are same. So by varying the separation d and the phase shift beta between two elements, the array factor can be, a value of array factor can be varied, and you look at carefully by variation of b and d, for same value of theta, AF can be different. So the radiation pattern can be controlled in that particular direction, which is narrated by theta. Let us look at one very specific example when the case of the separation of lambda by 4 and various cases of excitation, beta is equal to 0, the case 1, beta is equal to plus pi by 2, case 2, and beta is equal to minus pi by 2 is the case 3. So if we consider beta is equal to 0 and d is equal to lambda by 4, so your normalized pattern will look like this, cos theta. And how this expression has come? Expression has come from this resultant ET. So looking at this normalized pattern cos theta cos pi by 4 cos theta, we can now obtain nulls. Nulls are nothing but the direction in which the radiation pattern is 0. So setting the total field pattern is 0. So this equation, when we set it to 0 and find out corresponding value of theta for which this entire expression becomes 0, will be nothing but the location of the nulls. So either cos theta should be 0 or the second term should be 0. So when cos theta is equal to 0, we can easily derive theta n is a 90 degree. And when second term cos pi by 4 cos theta is equal to 0, that means pi by 4 cos theta n is equal to pi by 2. So that leads to theta n is equal to minus pi by 2, which is not possible, right? So theta is always positive, as we know, in a spherical coordinate system. Second case, when beta is equal to plus pi by 2, then my the total fill goes like this, and that way we can calculate all the different cases. Thank you very much for now.